Hello students, this is part 2 of chapter 3 and we're going to be working through chemical equations. This is a really important part because we're going to be looking at mole ratio in an equation to allow you to calculate between reactants and products. So this is also called stoichiometry and it's something that you'll be doing and using throughout the whole semester. The first thing I want to show you is just a different way to view a chemical equation. We've used formulas. We've seen methane plus oxygen giving carbon dioxide and water. I want you to be able to visualize this as well. So this is called a space filling model. It's a ball. The black ball is carbon, and there are 4 gray balls for hydrogen. Over here, a single red ball is an O. So on the left, you have in red the O2 molecule, and there are 2 of them. These all break apart. These bonds break and rearrange to give you carbon dioxide and 2 waters. So just notice the conservation of atoms of mass and the fact that atoms are neither created nor destroyed. So the number on the left matches the number on the right. And we've already talked a little bit about conservation of matter or mass. So this is key because we need to be able to balance equations if they're not already balanced for us. The power of the balanced equation is that you can see the direct relationship between reactants, such as 1 methane reacts with 2 O2s, or reactants and products. When you react 1 methane, you produce 2 waters. So this relationship is important. We're going to see that for every 1 of these guys, you can make 2 of these. Any multiple of that works. 2 methanes will give 4 waters. Avogadro's numbers worth will give twice Avogadro's here. So that's why this also works in moles. 1 mole of methane gives 2 moles of water. Let's first balance the equations. We have magnesium reacting with oxygen to give magnesium oxide. I can already tell just by inspection, I have 2 O's on the left. Notice the subscript. The subscript as well as coefficients in front will tell you the number of atoms there. I have 2 O's on the left, but only 1 on the right. So when I want to balance equations, I can never mess with the chemical formula itself. To balance an equation, I can only put coefficients or the big numbers in front. The reason is messing with the formula changes the identity of the substance. So let's balance this. First, I mentioned that there are 2 O's on the left, so I need to make 2 on the right. I can only put a big coefficient in the front of the whole thing. So what that does is gives me 2 O's, but it messed up the magnesiums. So now I have 2 magnesiums on the right, but only 1 on the left. So I correct that, and I further balance by putting a big coefficient 2 in front of the magnesium on the left. Now I'm done. Now it's balanced. Now I can see that, say if I reacted this, 2 moles of magnesium will produce 2 moles of magnesium oxide. Also, if I need to react 2 moles of magnesium in the lab, say I weigh out a wire, I have a certain amount, I could calculate the number of moles. I need half as many moles of O2. For every 2 moles of magnesium, I only need 1 mole of O2. You guys practice here, and you'll have more practice throughout the week. Here's an example where we have, in a car's engine, a hydrocarbon octane, C8H18. It's a component of gasoline. This is actually a liquid, and it mixes with oxygen from the air and burns to form carbon dioxide and water vapor. So this is a combustion reaction. You've seen this. Write a balanced equation. So pause this and try to do this. Write out all of the chemical formulas first and then balance it. When I write out the formulas, I just reproduce the octane here, plus O2 giving CO2 and water. Here, I gave some information as to the states of matter, liquid and gases. That's not necessary at this point, but eventually you guys will be doing that more. What I want to do is just look, is there anyone by itself, O2? I'm going to leave O, balancing O for the end because it's by itself. And if I put a number here, I don't mess up the other atoms. So looking at this, I tend to go for carbon first. I don't necessarily have to do that, but I see there's 8 C's on the left. So I need 8 C's on the right. There's only one molecule with C on the right here. So I'm going to put an 8 in front of carbon dioxide. Next, I'm going to balance the H's. I have 18 on the left and only 2 on the right. Water is a molecule with 2 H's and 1 O. So I need to balance it here. But whatever number I put here, I have to multiply by 2. So I need a number that's going to multiply by 2 to give 18. So that number is 9. 9 times 2 is going to give my 18 H's to balance the 18 on the left. Lastly, I balance the O's. Be very careful. Count how many are on the right. I see 8 carbon dioxides, and each carbon dioxide has 2 O's, so I have 16 here. But don't forget the water. I have 9. 9 times 1 O. So 16 plus 9 is 25 O's on the right. So on the left, what number times 2 is going to give me 25 O's? You could do 25 halves, or you could put 12.5. Obviously, I need a whole number there, so I'm not going to leave it like that. So the very final thing you do to clean it all up is multiply by the smallest integer to make this a whole number, and you have to multiply all of them. So if I take this whole thing and multiply it by 2 to get rid of the half, I multiply it by 2 at the bottom, look at my final answer. 2 octanes plus 25 O2s gives 16 carbon dioxides and 18 waters. That's your final answer. Let's now talk about stoichiometry. I showed you the magnesium oxide equation, and I mentioned 2 moles of Mg plus 1 mole of O2 gives 2 moles of magnesium oxide. So the coefficients give the relative numbers of reactants and products. We're going to use these as conversion factors to go between different types of conversions, between reactants or just reactants and products. Let's go through some problems here. So the first problem is how many moles of magnesium oxide, the product, can be produced from 1.5 moles of O2. The biggest tip I want to give you is never think that these big numbers in front are the real numbers in the lab. If I ask you how many magnesium oxides can be produced, don't say 2 because you see a big 2 here. These are just relative amounts. This could be 424, but we use the simplest whole numbers. If I ask you how much can be produced, you have to look at the real amounts used. I'm going to use 1.5 moles of O2. So you could just look at the equation and see, oh, for every 1 O2, I get twice as much product. So if I start with 1.5, I'm going to get twice as much product. I'll get 3 moles. Let's go ahead and just do that because that's an easy one here. You can see you're going to get twice as much, but sometimes the numbers aren't so easy and obvious. So let's go through this problem, starting with the 1.5 moles of O2. And the only way, anytime I ask you to go between reactants and products or reactants, you have to use mole ratio from the equation. For every 1, I get 2. So I need to go from moles of O2 to moles of MgO. So I put the moles of O2 on the bottom to cancel. And what numbers do I put? Look at the equation, 1 to 2. For every 1 mole, I get 2 moles of magnesium oxide. Moles of O2 cancel. That was mole ratio from the equation. So my answer is 3 moles of magnesium oxide. 3.0 because 2 sig figs. Let's do the second problem and see if you guys can do this. I would pause and try this problem yourself. How many grams of magnesium are needed to produce a certain amount of product? So now I give you the amount of product, 2.25 moles of magnesium oxide, but I'm asking you how many grams of magnesium do I need? This is a very common thing you have to do in the lab. A lot of times when I worked in the lab, I had to make a certain amount. Maybe my boss said, oh, I need 25 grams of such and such. So I would target 25 grams of this or whatever compound, and I would have to back calculate how much reactant I need to start with to get there. And so let's do that. Start with the 2.25 moles of magnesium oxide. You're going to go from moles of MgO to moles of Mg. Put the moles of Mg on the bottom to cancel. And what numbers do you put? Use the equation, 2 to 2. That's mole ratio from the equation. Moles of MgO cancel. And then now I need to go to grams, because I don't weigh out moles, I weigh out grams. Magnesium is a wire that you would weigh out. You could cut the amount that you need. So I go from moles of magnesium. How do you get to grams? The only way is molar mass. Put the grams on the top. Now what numbers do you use? It's always 1 mole for molar mass, and then read the atomic mass off the periodic table, 24.31 grams. Moles of Mg cancel, you get your product here. I'm sorry, not your product, your starting material, 54.7 grams of magnesium. Okay, let's do one concept checked for you guys. This is a little more lengthy because I have you write a balanced equation. Take your time writing out the charges and figuring out the formulas. Just to let you know, hydrochloric acid is HCl, and balance the equation. Pause and try to work out the lower problem as well, and I'll go through this. So here I put HCl. The manganese 4 oxide, manganese 4 means you have Mn4+. Don't forget, this has nothing to do with the number of atoms. 4+ must pair with 2 2- of an O. Add HCl, and you produce manganese 2 chloride, so you have Mn2+, which must pair with 2 Cls. Reacting with chlorine gas, I'm sorry, not reacting, producing chlorine gas and water. Balancing this, you would see that one tricky part is you add chlorines in these 2 molecules here. So you had to account for that, but basically a 4 in front of the HCl and a 2 in front of the water balances the equation. Working out this problem, I'm not going to work through this. We could talk about this later, but you start with your 0.45 moles of magnesium oxide, which is the starting material here, and you want to find out the grams of water. So you would go for every 1 mole of MnO2, you get and produce 2 moles of water, and then you can use molar mass. In the bottom next would be 1 mole of water to 18.02 grams of water, and you should get 16. All right, we're going to end here, and I will check back in with you guys later.